Hello, everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much, much more. My name is Saba, and today we're starting a new series of videos that are designed to help you understand the economics and the financial aspects of cryptocurrencies, one of the new asset classes that are very prominent in the news and that many of you have encountered previously. Perhaps you have mined or traded some of the coins we're going to talk about today. So, one of the simplest questions that one might ask with respect to the most prominent cryptocurrencies, such as Bitcoin or some of its forks like Bitcoin Cash or Bitcoin SV, uh, well, you can mine cryptocurrencies, but we all know that mining can be relatively costly. So, how to calculate the profitability of mining and if it's profitable to mine on these blockchains or not? To understand the concept, we need to first explore the various facets of the process of mining, what contributes to your payoff, your reward, and your cost as a miner. What do you have to do to successfully mine on those blockchains? And how much money would you need to invest in mining? And how much would you get out of your mining venture? Well, first, what I've done is I've downloaded uh, block data for Bitcoin, Bitcoin Cash, and Bitcoin SV for the 5th of April. So those are all the blocks that have been mined on those three blockchains on the 5th of April 2020. We can see that the number of blocks mined vary, as well as the time at which those were mined. Those were attached to respective blockchains, as well as the difficulty of mining. Those large numbers represent how difficult it is to solve the cryptographic hash functions that underpin the mining process, the solution to the puzzle that blockchains pose to the miners every single block. So we can already see that those numbers represent the so-called scientific format of data representation. What it means here is that E plus 13 here, for example, means that that number is roughly equal to 1.39 times 10 to the power of 13. So it shows you very evidently the magnitude of this number. Here we can see that the mining, the puzzles that you have to brute force using your mining hardware are much harder on the Bitcoin blockchain than they are in Bitcoin Cash or Bitcoin SV blockchains. We can see that the mining difficulty on Bitcoin Cash and Bitcoin SV are of the same magnitude roughly, but the difficulty of Bitcoin Cash is roughly 1.5 times higher than that of Bitcoin SV. So 3.4 and 11 zeros and 5 and 11 zeros. With mining difficulty on the original Bitcoin blockchain being almost 100 times harder than those on those two blockchains of forks. And that contributes to the fact that Bitcoin is much of a larger blockchain with more miners dedicating their computational power to solve cryptographic hash functions of Bitcoin. And that's also what can translate into a much higher coin value, coin market price for Bitcoin rather than those two altcoins, those two forks of original Bitcoin chain. Without further ado, we can estimate the hash rate of those three blockchains because, well, if you want to start mining on each of those chains, you need to understand how many other people or how much computational power already exists within the chain and how likely it is that you are going to be the lucky miner who has solved the cryptographic hash function first at each of those particular blocks. The more computational power exists within a particular blockchain, the harder it is to be the first to solve the puzzle. And it means that the higher is the hash rate, the lower is your probability of succeeding and obtaining this precious mining reward that is currently 12.5 coins for all of those 3 blockchains. But very soon, in roughly 4 weeks, there's going to be another reward halving with all mining rewards going down 50% exactly. So there will be 6.25 coins of Bitcoin, Bitcoin Cash, and Bitcoin SV per block. So that's also one of the factors that shaping investment decisions by miners and the dynamics of those coin prices. But without digressing into that too much, what we can do is we can estimate the hash rates of those 3 blockchains. And at first, it might seem impossible, or at least very hard to do so. Because, well, how would you know how many miners all over the world dedicate their computational power to solving those cryptographic hash functions for each of those blockchains? It's not publicly available. But what we can do is estimate, at least roughly, what the hash rate is by looking at how much time does it take, on average, to solve those cryptographic hash functions. Because, well, the more ASICs, the more mining hardware is engaged in every single blockchain, the more likely it is that the solution is going to arrive faster. So we can extrapolate this logic and guess how many ASICs are actually working on every single blockchain based on the time that it takes on average to arrive at a new block at a particular time period. And that is our best guess, our best approximation of the hash rate of the network at a particular time period. So to do that, we first of all need to figure out how many blocks have been mined on each of those 3 blockchains on the 5th of April to estimate the hash rate of the network on the 5th of April. To do that, we just need to count the number of blocks that have been mined on the 5th of April. So just count this column, count this column, and count this column. And we can see that on the 5th of April, there has been 175 blocks mined on Bitcoin proper, 145 blocks mined on Bitcoin Cash, 141 blocks mined at Bitcoin SV. So then we would be able to apply this formula to get the estimation of hash rate. What it says is, well, the more difficult it is to mine, the higher the hash rate is for a given block time, because, well, if the blocks appear at exactly the same frequency, but with more difficult cryptographic tasks to be solved, then it means that there is more computational power dedicated to the network at a particular time. And if holding difficulty constant, block time increases or decreases, it would correspond to decreases and increases in hash rate, respectively. Because, well, if it takes less time for the network to figure out a given task, a task of given difficulty, then it would mean that the amount of power, amount of hash rate dedicated to this particular network is higher, and vice versa. So that is the logic of this formula. Well, the design of all of those 3 blockchains is to maintain, in the long term at least, a constant block time of 10 minutes or 600 seconds. And by the way, we'll be talking about seconds here as the most common metric, the most common dimension of measuring hash rate is hashes per second. So we will convert everything into seconds to estimate our hash rate in hashes per second. Well, how do they arrive at this long-term equilibrium? Well, the logic that those 3 blockchains apply is conceptually the same, but technologically it slightly differs. What they do overall is that they adjust the difficulty of mining periodically to reflect this equilibrium value, this desired equilibrium value, this target of 10 minutes per block. So it would correspond to 1 block every 600 seconds, and it would correspond to 144 blocks per day. And as we see here, there has been more blocks than expected, than targeted, mined on the Bitcoin blockchain on the 5th of April, which means that the difficulty is probably lower than it should be. So the next time the difficulty adjusts, it will increase, most likely, to kind of restrain this block generating process. While for Bitcoin Cash and Bitcoin SV, the values of number of blocks mined within a day are much closer to the equilibrium value of 144. And we can attribute that to a number of various factors. We can see that the difficulty for Bitcoin does not change within our day, within 5th of April, while the difficulty for Bitcoin Cash and Bitcoin SV changes with every single block. That is what is different in the technological solutions of those two blockchains. The difficulty of Bitcoin Cash and Bitcoin SV adjusts every single block, while for Bitcoin, it does adjust only periodically, which means that the difficulty of Bitcoin Cash and Bitcoin SV would be more volatile at one hand, but on the other hand, they would be more successful in maintaining a roughly fixed amount of blocks mined every single day. Now, let's figure out the block time. Well, first of all, we need to know how many seconds are there within a day to figure out how frequently does one block arrive on average. So there are 24 hours in a day. Every day, every hour has 60 minutes, and every minute has 60 seconds in it. So overall, there are 86,400 seconds in a day. And that's the same for all three, obviously. Time passes universally. Average block time would be just the number of seconds within a day divided by the number of blocks mined on a particular day. So for Bitcoin, it would be slightly below 500 seconds. And for Bitcoin Cash and Bitcoin SV, that would be very close to the target of 600 seconds, or 10 minutes per block. Now, to apply this formula eventually, we need to figure out the average difficulty during the time period we investigate. We need to just average over the difficulties that were in place during our time period, so 5th of May. So for Bitcoin, obviously, that would remain the same as the difficulty does not adjust every single block. But for Bitcoin Cash and Bitcoin SV, that would basically reflect those changes that happen every single block. And now we can apply this formula to estimate the hash rate. Obviously, as those difficulty figures are very, very high, and adding an insult to injury, we are also multiplying by 2 to the power of 32, we won't have a very meaningful number if we just estimate it in hashes per second. That's why most of the time what you do is you estimate in other dimensions, namely you estimate it in kilo hashes, so thousands of hashes, mega hashes, so millions of hashes, and so on and so forth. So this distinction is very similar to what you have in units of data. So you have bytes, kilobytes, megabytes, terabytes, and so on and so forth. So here, at the current stage of blockchain development, it's most common to estimate hash rates in pentahashes. So a petahash would be 10 to the 15 of hashes. So you'll just need to divide the hash rate in hashes over 10 to the power of 15. So without further ado, what we can figure out now is 2 to the power of 32, as in the formula here, times the average difficulty on the 5th of April divided by the average block time in seconds. And to convert it into petahashes, we need to divide it by the 10 to the power of 15. We see that the hash rate of Bitcoin is 121,000 petahashes, or 121 exahashes, which are thousands of petahashes. Now we can drag this formula around and see that indeed the hash rates of the forks of Bitcoin, Bitcoin Cash and Bitcoin SV, are much lower than the one of the original chain. And some researchers speculate that, well, the differences in hash rates is what dictates the differences in coin prices. Because, well, if the hash rate is higher, it's more costly to mine on this particular chain, so miners would have to be compensated for having to dedicate more computational power to mining on this chain with a higher reward. And as the reward is fixed in the protocol in terms of miner reward, currently 12.5 coins for all three blockchains, reward halving is on the way, so on and so forth. Well, to compensate, market prices of respective coins should differ, accommodating for these differences in costs. And that would be the logic of cost-based pricing for cryptocurrencies. But without further ado, we can now consider various opportunities that we have, various options that we have to mine on those three blockchains. What is notable is that all three blockchains have the same cryptographic hash function dedicated to generating these cryptographic puzzles that miners then try to solve using their mining hardware. All three use the cryptographic hash function called SHA-256. So you can use the same ASIC, so application-specific integrated circuit, so a piece of hardware that is dedicated and is very good at solving a particular puzzle, mine potentially on all three blockchains. So the three most modern ASICs, so pieces of mining hardware, available to mine on blockchains that use this particular cryptographic hash function, are Antminer S15, Antminer S17, and Netminer S19. And the three characteristics of those ASICs that we are interested in are obviously their retail prices, which would correspond to our initial investment into our mining process, as well as their efficiency characteristics. Efficiency characteristics are obviously the hash rate of those particular ASICs, so the computational power 1 unit of hardware allows you to obtain, as well as the electricity consumption. Well, why is electricity consumption relevant? Well, electricity consumption is what constitutes your variable cost in terms of your mining operations, because your mining hardware constantly consumes electricity, and most of the time you have to pay for kilowatt hours of energy that you spend. So sometimes you might have a very cheap ASIC that would be less energy efficient, so it will have less of a fixed cost and more of a variable cost. And overall, it would be less efficient than a more expensive type of mining equipment that would be more energy efficient, so utilize less energy per hash. And the hash rate of those ASICs are usually reported in terahash per second. So again, that's 1,000th of a petahash. So the technical characteristics, as well as the current retail prices of those ASICs, can be found at various aggregators. For example, you can find it at asicminervalue.com. You could just find them at platforms like eBay or Amazon. Regardless, the data on those characteristics are readily available. We also need to make an assumption about what is the price of electricity, and it varies from country to country, because in some countries electricity is subsidized, in other countries it's taxed. Some countries produce electricity using their domestic resources, some generate electricity using imported natural resources, so that would correspond to varying electricity prices country to country. And that's what ultimately shapes the degree of mining activity intensity across the globe. In countries where electricity is cheap or heavily subsidized, such as Venezuela most commonly, and China as well, where it's cheaper than across the world on average, mining has become a very common activity to pursue. Whereas in developed economies where electricity is more expensive, or in oil importing economies where energy is more expensive, ultimately, mining activity is less profitable, and therefore less people decide to eventually pursue it. So, to estimate our variable costs and our expected payoffs, we need to first know how many blocks are expected to arrive on the blockchain within an hour. That's easy to answer. For all three blockchains, the ultimate long-term target is 10 minutes per block. So we would expect 6 blocks an hour to arrive at each of those three blockchains. Because regardless of what the hash rate would ultimately be, the difficulty would adjust so that to keep with this long-term target. Then we need to figure out how many kilowatt hours of energy we would consume using each of those three ASICs. So that's also easy to figure out. Well, because our time frame is 1 hour here, and this is in kilowatt hours, and this is in watts, we can just divide electricity consumption of every single ASIC by 1000 and get electricity per hour for each of them. By the way, we can carry out the analysis on the basis of one ASIC, just one ASIC, as this investment project potentially is infinitely scalable, or almost infinitely scalable. You can figure out your profit or loss per one ASIC, and then if you decide to buy multiple ASICs, you can just multiply your fixed cost, variable cost, and revenue by the number of ASICs you would like to purchase. So that's why this analysis is simpler, as you might otherwise think. And now, figuring out the variable cost of mining in dollars per hour, we need to multiply our kilowatt hour consumption per hour per ASIC. We need to multiply that by our electricity price. Here, we assume that our electricity price is 12 cents per kilowatt hour, which is a very common price of energy in the US. So we're assuming we are a US-based miner. You could change this to reflect the price of electricity in your own country. So we just log the column because electricity price stays the same, and we can see that, well, buying a more advanced ASIC, a more advanced piece of mining hardware, gets you a higher variable cost, but that corresponds to ultimately a much higher hash rate. For example, here, between Antminer S15 and Antminer S17, the hash rate doubles, while the electricity consumption does increase, obviously, but not to that great of an extent. So it means that ASICs become increasingly energy efficient, and that would correspond partially to ever increasing hash rates of major blockchains. When you move from Antminer S17 to Antminer S19, your hash rate also almost doubles, while your electricity consumption increases but not proportionately. So that is what corresponds to increase in energy efficiency of ASICs, and to slowly phasing out of older ASICs as more energy efficient, more profitable pieces of mining hardware become readily available. Now, what we can do is we can estimate the profitability of using each of those three ASICs at each of the three blockchains we consider. So, first of all, we already have the variable cost, and that would not change regardless of the blockchain we are mining on, because it only depends on the ASIC's electricity consumption as well as on the electricity price. That doesn't vary blockchain to blockchain. What does vary blockchain to blockchain is the probability of success. The probability that you, having bought an ASIC and started mining on a blockchain, would be lucky enough to be the miner who eventually guesses the cryptographic puzzle first and gets the right to attach a new block to the blockchain. And that rewards you with 12.5 coins of a respective blockchain. So what is the probability of success for Antminer S15, for example, while mining on Bitcoin blockchain? Well, to figure it out, we can just divide the hash rate of Antminer S15 by 1000, because, well, this hash rate is in terahatches and we need it in petahashes. And then we need to divide it by the hash rate of, and we need to lock that as our hash rate stays the same ASIC to ASIC. And we see that the probability of success by just buying one ASIC and starting mining on the Bitcoin blockchain is very low. And it's also very low for other ASICs, but again, it's increasingly higher as the hash rate of those ASICs increase. Then, using this probability of success, we can figure out our expected revenue that we obtain within an hour. So to figure out the expected revenue per hour, what we need to do is first estimate how much money will we get if we are the lucky person who finds the new block and solves the cryptographic puzzle first. So first of all, how many blocks? Well, 6 blocks per hour. And we need to lock that because, well, it's the same for all 3 ASICs. Then we need to multiply it by the reward, and the reward is 12.5. 12.5 coins of the blockchain we're mining on. Then we need to convert this payoff into dollars. Well, because we pay for electricity in dollars, we purchase ASICs in dollars, so we need to express our expected revenue in dollars as well. So we need to multiply that by the market price of the coin we're trying to mine. But that's what would happen in the best case scenario. We need to multiply it by our probability of success, because if we fail, we get nothing. We mine no coins and have just endured the variable cost for nothing. So we need to multiply it by the probability of success. And it gives us 12 cents per hour of expected revenue if we use Antminer S15. Drawing it around, we can get expected profits for all 3 ASICs, and figuring out net profit per hour, we just need to subtract the variable cost from our expected revenue. And here we can just lock the variable cost, the row for the variable cost, because again, the variable cost does not depend on the coin we're mining. And we see that for Antminer S15 and Antminer S17, the net profit is negative. So we haven't even accounted for the cost of purchasing an ASIC yet. So it means that we are losing by trying to mine using these older ASICs on the Bitcoin blockchain. The only ASIC that is capable of generating a profit on the Bitcoin blockchain is the most recent one available, Antminer S19, that has been released very recently, namely in December 2019. Now, what we can do is we can figure out the profitability in percent per hour, so our internal rate of return, basically, of this mining project. To do that, we just need to divide our net profit per hour by the retail price of the ASIC that we're concerned with. And this is our fixed cost, so it doesn't change blockchain to blockchain. It only depends on the ASIC you choose. So we can log the row over here and see that our profitability is, again, negative. And it's negative for both Antminer S15 and Antminer S17, and positive for Antminer S19. And then we can just annualize this profitability by applying the geometric scaling. So 1 plus the profitability per hour, we need to raise it to the power of how many hours there are in a year. So there are 24 hours in a day and 365 days in a year. And then we subtract 1 and get very unattractive, let me say like that, annual profitability of this outdated ASIC on the blockchain of Bitcoin. And the only, again, ASIC that generates a positive internal rate of return for Bitcoin is, again, the most recent ASIC. Now we can apply the same logic to Bitcoin Cash and Bitcoin SV and see how does it correspond to the results we got for Bitcoin. So again, probability of success for Bitcoin Cash, well, what we can do is we can just copy this formula, paste it here, and instead of the hash rate of Bitcoin, take the hash rate of Bitcoin Cash. Drag it around and see that the probability of success is much higher than that for Bitcoin because, well, the hash rate of Bitcoin Cash is much smaller. Then for expected revenue per hour, we still can just copy that over here, and instead of this probability of success, select this one, and instead of the coin price for Bitcoin, take the coin price for Bitcoin Cash, and then drag it around as well. And for net profits per hour and profitabilities, we can just copy those cells across and see how do the results correspond to ones we obtained for Bitcoin. First of all, Antminer S17 almost breaks even as compared to generating a significant loss if we think about Bitcoin Cash with respect to Bitcoin. And Antminer S19 is even more profitable as the expected revenue per hour is substantially higher. Now, we can do the same for Bitcoin SV. Copy this formula, paste it here, but change the respective hash rate, drag it, and get even higher probabilities of success corresponding to a lower hash rate. And expected revenue per hour, again, we can just copy this formula and adjust it to Bitcoin SV blockchain. So change this probability of success and change this hash rate. And then those cells we can just copy across and see that for Bitcoin SV, the profitability is greater still. What would it mean in terms of market equilibrium? Well, as the cryptographic hash function for all three blockchains is exactly the same, miners can arbitrarily switch between the three blockchains and go to a blockchain that they find most profitable right now. So as Bitcoin SV and Bitcoin Cash are currently more profitable than Bitcoin, then you would expect a bunch of miners that use Antminer S19 to switch to Bitcoin Cash and Bitcoin SV. What would it mean for the hash rate? Well, it would reduce the hash rate of Bitcoin, it will increase the hash rate for Bitcoin Cash and Bitcoin SV, and that would bring the probabilities to equilibrium. Obviously, that simple logic doesn't account for the expectations of future price volatility, because obviously, if the price changes and you have obtained the reward in the native coin of a particular blockchain, then you can obtain less of revenue in dollar terms. So that might be a kind of a risk premium that is incorporated in these figures. For Bitcoin might be perceived as a more stable cryptocurrency in terms of value. That might be a part of the story. A point that I would like to make at the end of this video is, well, that these expected revenues per hour are not stable across time because you have very low probabilities of success. So risk-averse miners are generally expected that any people that engage in investment decisions are generally risk-averse. Well, this expected revenue is not that attractive because sometimes you will spend days, months, or even years without obtaining any reward, and sometimes a large sum of money will just drop onto you. So a common practice to avoid this risky structure of your payoff is to consolidate into mining pools. When a bunch of miners self-organize and basically bring their computational power together and agree that if any one of them obtains the mining reward, any one of them is lucky enough to get the payoff, they would share the mining reward proportionately to the computational power devoted to the mining pool among themselves. And that what brings the riskiness of this project down, and that's what explains the prominence of mining pools in the mining activities for most major blockchains. Well, are there any risks associated with this structure of blockchain functionality? Well, That's something that we'll discuss in future videos. As for now, thanks very much for your attention. Please leave a like under this video if you found it helpful. In comments below, please leave any suggestions in terms of future videos on cryptocurrency related topics. And don't forget to subscribe to our wonderful channel. Thank you very much and stay tuned.